Professor. I'm Dennis from Makere. I'll be sharing this next session, and the rapporteur is Dr. Alex Ogacho, a very strict timekeeper. I guess all the presenters are in. Our first presentation will be from Jorim Obila. Obila, are you there? Are you there, Mr. Obila?
Yes, I'm here.
Oh, yes, yeah. Maybe organize your presentation. We have 15 minutes to present. As we come in, Obila is from the University of Nairobi, Kenya. He will be presenting to us something on stability and efficiency of improvement of planar 3D stroke 2D tin-based peroxide solar cells.
Can you see my screen?
Yes, maybe you can increase it a bit.
I think it is much increased, so maybe check from your end.
It's clear.
Okay, thank you. So I'm Jory Mobila from University of Nairobi. My supervisors, Dr. Alex Ogacho, University of Nairobi, and Dr. Elijah Ayeta, University of Nairobi. So I'll be talking about efficiency and reproducibility improvement of 3D stroke 2D tin-based perovskite solar cells using anilinium hypophosphite. Now, before we go further into the discussion, maybe the participants can just look at some of these abbreviations because I'm going to use them much. Some of these names are not easy to pronounce several times. You might easily slide and it will be the story of the session. Okay, now we go to the background. Now in the background, I'm dealing with organic, inorganic, hybrid perovskites. Now this kind of perovskites have attracted much attention of researchers due to their good optoelectronic properties. And this kind of perovskites have the structure of AbX3, where A is a monovalent ammonium cation, which can be Ma, Fa, or Fa, and then B is a divalent cation, which is lead, tin, or germanium cations. Then you have X, which is a halide anion, which can be iodine, bromine, or chlorine. Now, this kind of perovskites, people have done a lot of work on it, and the most researched one is Ma lead iodide. Now, because of too much work on this kind of perovskite, an efficiency of up to 25% have been achieved. This one is giving people hope that one day maybe this kind of perovskites can lead to a fourth solar cell technology or generation. But now the main challenge is the use of this lead component here. Because if you look at this figure I'm having here, if this material gets into contact with water, you can say we have several byproducts. Now, these byproducts we have here, the most dangerous one, which is now lead iodide plus again water. This one again, if it dissolves in water, again it forms another, now just real lead, which is poisonous for anything. And as you know, water can always be running, maybe into rivers, plants absorb it and everything like that, that can cause more harm to human lives and even to the environment. So there is need to change this kind of material. So instead of having lead, we need to change it. But now the main challenge is that if we are changing lead, we already know that this material here is having best optoelectronic properties. Then that material that we are using to replace lead must maintain this properties here. So some of the substitutes here are these ones here, but our main interest is the tin as a substitute for lead. This because tin will maintain all the electrical properties and optical properties of this material. And sometimes it has even better properties than the lead perovskite. Now, here we have some of the properties that make tin perovskite attractive to researchers. We have high absorption coefficient, high charge carrier, mobility, among others. Then we have challenges facing tin perovskite. As I've told you, it has very good properties, but still it has so many challenges, like it has low PC, a low power conversion efficiency, then you have poor reproducibility. All these ones are all caused by the ease of oxidation of tin 2+ to tin 4+. And again, we have another cause for this one, which is fast crystallization. Now, this fast crystallization means that this material, if you are depositing it, chances of it completely covering the substrate are very minimal. And therefore, a number of things has to be done to improve this so that we can have higher efficiency and also reproducibility can be made easier. And the main reason for poor reproducibility is this one here. One thing about this research on tin perovskite is that it is not very easy to control these conditions to match the conditions of other group or other researchers. Like if you are working on, maybe if you want to copy maybe somebody's work, it's not easy to get even the exact efficiency because the conditions are different and the oxidation will depend on much on the conditions. Then we have now strategies to improve now the PC of tin perovskites, where the first, as I told you, we have crystallization rates very fast. So it affects the morphology. So the first part is to optimize the film morphology. And in doing this one here, people have used solvent engineering where they mix maybe DMSO and DMF. I told you to look at the abbreviations early. It's not easy to mention those things. So we have DMF and DMSO. They mix them at a ratio of DMSO 1, DMF 1, 4. So 1 to 4. Then another thing they use now is called anti-solvent dripping during deposition process. Now, using the anti-solvent dripping method and the mixing of the solution method, you'll discover that at least the coverage of the film will be better. And thus, we are going to reduce chances of having poor film morphology or having a film with so many pinholes. Then you have another second thing we can do, which is adjusting the composition of films. Now, in adjusting the composition of the films, this one we can mix the ammonium cations so that you can have MAFA mixed, or we can introduce even other things, which is here, but I don't want to talk about it here. Then we have the third one, which is modification of the device structure. Now, normally people are researching on the regular structure, that is the NIP structure. But here we are now introducing the PIN structure. The reason being that in the regular structure, people use the spiral, which is not very good. Spiral has some salts like lithium salts, cobalt salt, which are vulnerable to moisture. And that moisture, if they absorb that moisture, it is going to affect or degrade our perovskite. And so the best way is to try and avoid that spiral. And that's why we have to modify that structure. Then the next one is designing a 2D to 3D film structure, where in this case here, 3D has the structure of ABX3. And then if we now introduce a bulky ammonium cation like PEA, EA+, and then BA+, we are going to have something like 2D to 3D. But this one is mostly possible if we introduce these bulky ammonium cations at trace amounts, not in large amounts, because if we introduce in large amounts, it will affect the electrical properties of the absorber, which is not good for the solar cell. Then another part is using the reducing agents. Now, this figure here is a case where we are now trying to have the 2D stroke 3D structure. Now, this PAI, if we have it in a trace amount, what normally happens is that it will embed itself along the grains of the perovskite or of the 3D perovskite, so that it forms like it encapsulates the grains or passivates the grain boundaries. The main reason for doing that is because such a material is hydrophobic in nature. In other words, it is not easily affected by water. So it will form like some block on the grain boundaries. You have to know that along these grain boundaries, even moisture or oxygen can enter through. And so if we block them, then it means the perovskite generally will be stable. Now, using reducing agents, stroke additives, we have the main ones are always tin chloride and tin fluoride. Now, if we use tin fluoride, we can maintain or we can reduce the oxidation rate of Fa or Ma tin iodide or the tin perovskite. But the main challenge is that if this one is used in excess, it forms now some aggregates on the surface of the films. These aggregates here will also just reduce the performance of the cell because they act like some charge trap centers. Now, what people are now trying to do is that, yes, we are still going to apply them, the tin fluoride and tin fluoride, but we have to get rid of these aggregates or these other phases that are formed on the surface. And that leads to introduction of another additive, which is called a co-additive. Now, the major co-additives that have been used, people have seen that they will react with these phases here to form a complex. Now, this complex here can either passivate the surface or passivate the grain boundaries. Now, another thing here is an example of what is happening, how one of the co-additives, that is ammonium hypophosphite, can be used to reduce tin 4 in the perovskite. And this is the equation. Now, normally what happens sometimes, like here we have a group that used ammonium thiocyanates with sodium tin fluoride. Now, after using this, they also employed the PAI. Now, just as what I've told you is that this PAI can passivate the grain boundaries. Also, using this co-additive and the tin fluoride, this one also will form a complex that can either passivate the grain boundaries or passivate the surface. And since this one is already passivating either the surface or whatever, then we are going to have such a film which does not really have grains. It is just there. But the best thing about this film is that the number of pinholes are reduced. And so we are assured that at least the stability of this kind of device will be improved. Another thing about these co-additives is that they improve the crystallinity. And we know that if crystallinity is improved, then chances of charge recombination is also reduced because trap size have also been reduced. Now, this is just another example of what happens if we introduce a co-additive with the normal additives used. Now, this is what we did now. We used now the PIN structure where our P or the whole transporting media is P dot. Then we had the electron transporting media, which is PCBM, and then you have DCP, which is just like creating some ohmic contact between the PCBM and AG. AG is silver. So we have our perovskite, where the perovskite here is in this form here. We have Fa50, Ma50, we mix the two, and then the tin iodide. So from here, our antisolvent that was used is CB, and then the co-additive is HZ. Now, we are trying to say that this thing here will form a more stable, an improved stability of this kind of perovskite, because if we look at all the people have done, people have tried mixing these two to get an improved stability, and also to introduce this one here to passivate the grain boundaries and everything to improve the stability. Then this one here has been used like the anti-solvent to improve the film coverage, which even in our case here, our film coverage was very good. Now, from the same images of our absorber, if we just have the tin fluoride incorporated into our precursor solution, we deposited it, and from what you can see that if we use the anti-solvent, the pinholes may be there, yes, but they are very minimal. Like I can just see like just a few. You can't see many. Of course, don't confuse the pinholes and potholes. There are potholes and there are pinholes. Then another thing here is that using just this tin fluoride, you can see these white spots. These white spots are just like what I showed you earlier. And these are just like some aggregates, or they are just other phases forming on the film surfaces. These phases here will affect the film, the solar cell performance, and chances are high that the VOC of this kind of film will be reduced, and maybe the performance and everything will reduce. Now, if we now introduce, after optimization, if we introduce now 5% AHP into this precursor solution, we had now such a film. Now, if you look at this film here, the film is very smooth. And maybe I cannot talk about the smoothness, but we cannot see these white spots. And also maybe we can also not see pinholes. They are not there. Meaning that by introducing this one here, we improve so many things about this kind of perovskite, this kind of absorber. Now, what happened is that from here, we alleged that this AHP will be reacting with the tin fluoride, which is forming these other phases on the surface, to form some complex that can cover the surface of the film. And we used now the FTIR measurement to investigate the truth about that. And our AHP has this kind of structure, which is having now the P-O double bond there. Now, this P double bond here, O double bond, from the FTIR measurement, it forms around this area here, this region, 1320 to 1140. But after reacting with the tin fluoride, it shifts now to 1085, which we saw that it is very true. Like here we have, you can see this bump here. The upper one is just for tin fluoride alone from the FTIR. Then after mixing the two, we now had this one here. And also, if we introduce it now into the perovskite, we have this one here. The lower graph here, we have just perovskite without perovskite containing tin fluoride without the HP. And this region here, you can see we don't have anything. It's just flat. But after introducing it, we now have this one here, which is just as a result of this double bond here reacting with the tin fluoride. Now, that tin fluoride, the complex forms, and even after annealing, that complex is still left in the film, and that is why maybe we have like some very compact film like that. Then now we went to the XRD measurement. Now, in the XRD measurement, we find that our film here is very crystalline. The upper one is what we are dealing with. We have Fa50, Ma50 tin iodide, which is the upper one. Then we now did the individual XRD measurement of the components, which is Ma tin iodide and Fa tin iodide, to investigate what is really responsible for this high crystallinity. Now, if you look at the Fa tin iodide, its crystallinity is very poor. No matter what you do, this thing is just misbehaves anyway. Now, if you go to Ma tin iodide, it has high, the crystallinity is very good. And now one other thing is that it has just one orientation, like we have 100, 2004 MA, meaning this one here is just oriented parallel to the grain, the substrate. So if we mix this and this, we have even improved properties, like we have now improved crystallinity. So that is one advantage of mixing the two, and that is one motivation of mixing the two. But after mixing the two, we have these other small peaks here, which are just like, these ones are just because of the PAI that we introduced.
Jorim?
Yes, sir.
You have 3 minutes.
No problem. Then now from there, we tried investigating the stability of the two films, which is having the tin fluoride and the HP plus tin fluoride. And we discovered that after exposure to air for some time, the HP showed better peaks or better crystallinity than just that. So it means that if we mix HP and that one, we are going to have better stability. Now we tried now the absorption measurement, and this is what happened. You can see that if we mix tin fluoride and HP, the absorption is a little improved just because we got rid of those other phases. Then if you look at now the PL measurements, the PL measurement of just tin fluoride alone, if we have tin fluoride alone in the film, is a little lower than if we have both. This one is because this one already we know it has some phases and whatever properties of the film. So if we get rid of those other whatever phases, then we are going to have this improved. Then now go to the solar cell characterization. After discovering that the properties of the absorber, if we have the HP mixed with the tin fluoride is better, we now made our solar cells and investigated their electrical properties. And from here, you can see that just by eliminating those other phases, we can have improved VOC. And also, I think we also have improved fill factor. Now, it means that if we have now better or good films, we can have better solar cells, and also the stability will also be improved. Now, this one is just a confirmation of this. There's nothing much. Then I wish to acknowledge ISP, which actually took part in funding this, and then Professor Aduda for helping me get this opportunity, and then RCF, which is now the one going to respond. Then you have Professor Fengao, Linköping University. Thank you.
Okay, thank you, Jorim, for your presentation. I think I may ask for some 2 or 3 questions before we call the next presenter. Then more questions may come after. Anybody with a question for Jorim?
Oh, chair of the section. So sorry for disrupting. Questions will come at the end after all the presentations.
Okay, so okay.
Program.
Okay, let us go to the next presenter.
Okay, let me start sharing.
Hello.
Yes, please.
Dr. Okello?
Yes, Prof.
Yes. Just sorry for interruption. Questions and discussions will come at the end after all the presenters have presented. As per the
yes,
program.
I've got you clearly.
Yes. Okay. So we just have the next presenter.
Okay.
I'll stop sharing.
And stop sharing.
Yes.
Next is our next presenter is Mr. Alex Okello. Alex, are you there?
Hello.
Yes, Alex is there. You can organize your presentation.
Can I
Alex,
share my?
Yes, please share your presentation, your screen.
Yes, there it is. Are you able to see it now? Hello.
Yeah, you put it in the presentation mode.
Is that okay?
Is very okay there?
Okay.
Yeah, you can go ahead. Introduce yourself and now you proceed.
Yes, I'm called Alex Okello, a PhD student at Makerere University. The supervisors are Dr. Dennis Okello of Makerere, and then I have Dr. Namukobe Jane, Department of Chemistry, Makerere University, and Professor Julius Mwabora. The topic there is the influence of anthocyanins on electron transport of dye-sensitized solar cells. To begin with, I'll look at the structure of the dye-sensitized solar cells here. It consists of the anode, which usually has TiO2 deposited on it, and then the cathode consists of platinum, and all these materials sit on FTO glass substrate. On the diagram on my left here, I've shown the mechanism of how a solar cell works. In operation, the dye absorbs light, and it is excited, and then electrons are promoted from the highest occupied molecular orbit of the dye to the lowest unoccupied molecular orbit of the dye, and consequently, an electron is injected into the conduction band through process 2. Process 3 indicates the movement of electron through TiO2, and then process 4 indicates the injection of electrons to FTO glass substrate. As that happens, the dye receives an electron from the redox couple, and in a way, the hole will eventually move from the dye to the redox couples through process 5. Process 6 indicates the movement of the holes through the electrolyte, and eventually the whole process is completed by the dye regeneration at the counter electron through process 7. Process 8 and 9 indicate electron loss routes, which happen in a dye-sensitized solar cell. Now, the problem here is that dye-sensitized solar cells have very low efficiencies compared to others such as silicon-based solar cells. However, it has been reported that an efficiency of more than 12% of recent using ruthenium-based dyes are achievable. Here, the objective is to investigate the influence of concentration of anthocyanins on electron transport. Materials and methods. Here, I used fresh flowers of acanthus pubescens, which was macerated in methanol acidified with 0.5% trifluoroacetic acid. And then it was partitioned against ethyl acetate. And this diagram down here is an indication of the partitioning process. The upper layer contains chlorophylls, carotenes, and many other pigments which were in the flowers, while the lower part contains the anthocyanins which we were interested in. So we went ahead and separated using this separating funnel, and then after we concentrated the extract, and then we divided the extract into 4 different volumes, each of 5 mils. To each of these, we added these volumes of methanol acidified with trifluoroacetic acid to obtain 4 different volumes, but at different concentrations. At this stage, we have the solutions which we are sure that they are different concentrations, but we cannot tell which exact concentration are those samples that we have. So we went ahead and determined their absorbance nevertheless, and then to determine their concentration, we used a standard which also contains anthocyanins. We measured the following masses, then dissolved them in methanol acidified with trifluoroacetic acid. And then we went ahead and also measured their absorbances. And afterwards, we plotted a graph of absorbance against concentration. In this case, we have an equation which relates absorbance to concentration. We therefore used this equation to calculate the concentration of the samples which we had prepared, and we obtained the following concentrations. We also went ahead and we studied the absorbance properties of the samples we had prepared. And here we have the spectra, which is plotted on the same axis. As you can observe here, all the peaks are around 530 nanometers. And also you observe that the highest concentration, for example, the blue curve, it has the largest area of all the curves there. That indicates that it absorbs more photons compared to the rest. Then we went ahead and we fabricated the solar cells. We applied TiO2 on the glass substrates using Dr. blade, then annealed and dipped in anthocyanins and left it to stand for 16 hours. The platinum precursor was applied using a brush and annealed to activate platinum. And then we went ahead and assembled the solar cells. We then went ahead and measured the performance of the solar cells which we had fabricated. And from the curves, it is clear that on this axis we have current, we are able to see that short circuit current increases with concentration. Likewise, the open circuit voltage also increases with concentration, and also the fill factor, which is actually the area under these curves here. We also observe that as concentration increases, the curves tend to circulate. They become closer and closer to one another. Those were the observations I was able to make in my measurements. I then went ahead to explain why those ones happen the way it is. I observed that short circuit current increases because of increased absorption of more photons, and thus there are more photogenerated electrons which could be transported to the contacts of the solar cells. To explain the increase in VOC, that is the open circuit voltage, I considered this equation here, which it has terms. This first two terms here is called the quasi-Fermi level, and usually N, which is the number of electrons injected in the conduction band of TiO2, is less than the density of states. Now, as N increases, this term here usually goes to 0 because of this logarithmic term here. So eventually at a high concentration, you'll have approximately VOC is given by this relationship here. Now, this indicates a shift in energy level of electrons in the conduction band of TiO2. We also note that fill factor and conversion efficiency are both functions of open circuit voltage and short circuit current, and so they will also increase. So we conclude therefore that the main reason for the increase in VOC, it is because of the shift in the Fermi level of electrons in the conduction band of TiO2. However, there are other factors which also affect the Fermi quasi level. And these are the types and the number of anchoring groups that attach themselves to the surface of TiO2. Here I considered the structure of anthocyanins which were used. In a previous work by Namukove in 2006, she analyzed exactly the same flowers, and she was able to isolate two types of anthocyanins. Here she had the cyanidin-3 rutinoside, and she also had the cyanidin-3 glucoside, and this was 3% and the other one was 97%. When you look at the structure of these anthocyanins, the attaching groups there are the OH groups, and they use these groups here to attach themselves to the surface of TiO2. This structure here is simply the sugar, which is attached to the structure of anthocyanins, and it will also play a part because itself is a molecule which will greatly influence the energy level in the conduction band of TiO2. The same applies to this structure here, which is a sugar. Now, on the circulation of VOC and IC, I attributed this to the nature of materials which were used to construct the solar cells, possibly as concentration of anthocyanins increases, we tend maybe towards the maximum possible VOC and I short circuit. Then there is also steric hindrance on the surface of TiO2 as concentration of anthocyanins increases. Steric hindrance is a situation whereby when other molecules come, those which arrived first prevent those other incoming ones from attaching themselves to the surface of TiO2. The resultant effect is that it affects the rate at which charge is injected into the conduction band of TiO2, and as well as the Fermi level of electrons in TiO2. Now, to explain those further, we did electrochemical impedance spectroscopy on the solar cell. And here I began with a brief theory of what happens in electrochemical impedance spectroscopy. Usually, unapplied potential to the solar cell is perturbed by a small signal sinusoidal wave, and then the EIS will output body plots, which is a plot of real impedance versus the frequency. And then we have Nyquist plots, which is a plot of imaginary impedance versus the real impedance. The solar cells are then modeled into a combination of resistors and capacitors so as to match the experimental data from the EIS. Values of R and C obtained are then used to study electron kinetics in the solar cells. Usually, for a dye-sensitized solar cell, you will have 3 semicircles. On the upper diagram, I have what is called the general transmission line model of a dye-sensitized solar cell. This side, as you can see, this one is called, this part here is the cathode, while this side here is the anode. The yellowish part represents the electrolyte in the solar cell. Now here we have recombination resistance at the counter electrode, and then here we have the Helmholtz capacitance. Now the time constant between these two will give this small semicircle on this side, while this semicircle here is represented by what is called the Warburg impedance, which is the resistance to flow of ions in the electrolyte. And then we also have a recombination resistance at the anode, and then we have the chemical capacitance because of the double layers of TiO2 and the FTO glass substrate. So usually the EIS will give a curve which is like this. However, the However, the visibility.
Alex,
Yes.
your time is almost up.
Let me move faster. Now, in our experiment, we observed the following curves, and then we used this circuit here to fit the data. R1 is the series resistance. R2 is recombination resistance at the cathode, and R3 is recombination resistance at the anode. These ones are called constant phase elements because they behave as capacitors as well as resistors at the same time. And this one represents the Warburg impedance, which we talked about earlier. Now, here we are unable to observe all the three semicircles because the visibility depends on the applied voltage and also on the time constants between this part and that. Sometimes they absorb one another. Now, we are able to observe that recombination resistance increases with the concentration, and so does this frequency here at the maxima. Now, we went ahead and also looked at the expression for recombination resistance, which is given by these terms here. And of importance here is that R naught is defined as the activation of recombination. The only constant, the only terms which are not constant here is Kr, which is the rate constant for recombination kinetics, and then this. The rest are all constant in a solar cell. So we also observed that recombination resistance depends on this term mostly. So when there is a shift in the Fermi level of electrons in the conduction band, so there will be changes in recombination resistance. We went ahead and computed electron transport parameters. Here we have the transport resistance, which is the sum of series resistance plus recombination resistance at the cathode plus recombination resistance at the anode, and you see that they increase with concentration. We have electron lifetime, which, as you can see, is it also increases with concentration of anthocyanins. Electron lifetime is defined as the time electrons stay before recombination occurs, while this is chemical capacitance and this is electron travel time. That is the time the electron takes to make one complete cycle throughout the cell. And this side we have electron collection efficiency. We observe that as recombination resistance increases, more and more electrons will live longer because of that increase in resistance. That is why we have an increase in electron lifetime. And because of that increase, there are more electrons which are collected at the cathode, having transited the entire cell throughout. And so the electron collection efficiency increases. In conclusion, increase in concentration of anthocyanins results into more photogenerated electrons. That increase in the number of photogenerated electrons results into increase in short circuit current, increase in open circuit voltage, and then increase in recombination resistance. Short circuit current, open circuit voltage, and recombination resistance are all linked to shift in the Fermi level of electrons in the conduction band of TiO2. In acknowledgement, I would like to thank the International Science Program through Msseesa for their support, and I also thank the African Center of Excellence in Materials, Products Development and Language Technology, MAPRO-NANO at Makerere, and of course, University of Nairobi in general, and the technical team in University of Nairobi Solar Lab. Many thanks for your attention.
Thank you, Alex, for your presentation. The question will come later. I think we move on to the next presenter, that is Ms. Nancy Obare. If you can end the screen sharing, Alex. Nancy, are you there? Nancy?
Yes.
Yeah, you're the next presenter. Can you prepare yourself and share your screen? Nancy's from University of Eldoret. She'll tell us more about her presentation. Please go ahead and share your screen.
Maybe how to get this.
Yes, it's clear?
Is it okay?
It's okay, you can go on now.
Okay.
Introduce yourself and proceed.
Okay, I'm Nancy Obare. I'm a student of Msseesa University of Science and Technology, Eldoret North. My supervisors are Dr. Maxwell Mageto and Dr. Victor Odari. I'm going to talk about in this paper optical, electrical, and structural properties of copper antimony sulfide films deposited by spray pyrolysis technique. We realize solar energy is an important and sustainable renewable energy source that is growing rapidly as an energy where people are demanding on it as an energy. Among the various types of solar cells that are developed so far, the thin film photovoltaic is the most viable technology that is used to visualize the photovoltaic cells, which is currently relying on silicon-based solar cells. So therefore, with these energy demands, it has led for researchers to look for another technology which is less expensive with toxicity level being low. We are looking for a material with less toxicity, cost of production that is low, and that might be available. Therefore, copper antimony sulfide is an important semiconductor with a narrow band gap showing a potential of application in various optoelectronic devices such as infrared detectors and solar cells. So the focus is to look for an absorbing material that is good, that can absorb and has a band gap. Therefore, copper antimony sulfide has a band gap of 1.5 electronvolts, which is, and also has what high absorption coefficients. Therefore, efforts have been made. I deposited copper antimony sulfide thin film on a glass substrate using spray pyrolysis technique. Therefore, my age, why am I studying on this? Because the current thin film solar cells technology based on canadium thelamine and the copper indium selenites are some. Therefore, I see as thick at abundance absorber material that can be used as a thin film in solar cells. And it also shows high absorption comparable to the advanced materials. Hence, it has attracted interest for further studies. So this is study will yield a better understanding of the properties of thin film of copper antimony sulfide and open a new possible applications areas. I chose spray pyrolysis technique because it is fast and easy to operate in preparations also it is cost-effective methods, which will translate to lower production costs. Okay, how did I prepare it? I used capric chloride, antimony chloride, and the urea as precursors, deionized water, and isopropanol was used as a solvent. I cleaned the glass substrate. Then I deposited it at a molar ratio of 0.1 to 0.1 and 0.2. That's 0.1 copper, 0.2 antimony, 0.1 antimony, and 0.2 sulfur. The morality of sulfur was high. This is generally to cater for the stoichiometric matrix because it sublimes at higher temperatures. Actually, above 444 degrees Celsius, sulfur will have to sublime. The schematic view of the spray chamber was this one. That's where I laid my substrates around there. This is where I put my substrate. That was my glass substrates. This is a hot plate. Then you hear that, and also there is air that was coming in, generally the oxygen, and the solution was passing through these valves. Then it was sprayed. At the temperature was kept constant. The temperature was varied. That's from 190 degrees. Then 300, I deposited at 190, 300, and 350 degrees Celsius, while maintaining the flow rate at 2 ml per. Then the pressure was kept at 3.5 pascals, and the flow rate also, the distance between the nozzle and the glass substrate was maintained at 15 centimeters. So I did characterization of my samples, that's the thin film samples that were prepared of copper antimony sulfide. I used the XRD that's the XRD patterns of the film, that's Bruker differ, that's of that wavelength, that's 1.54059 Armstrong. And then I used the energy dispersive X-ray fluorescence, that's EDXRF, to determine to determine the elemental composition of the thin films that I prepared. I used the same, the cis cross beam 540, to determine the structure, how it was laid, the structure of the thin films. I also used I used the UV-Fizz spectrophotometer to determine the optical properties. I simulated the data of the optical properties using Scout 2 software to determine the electrical properties. From the work, I did the analysis, my results of the structural properties on the XRD patterns of the thin films. That was done at that wavelength, that's 1.54059 angstrom, and the scan range, at the scan range of 2 theta from 20 to 80 degrees. And then they were, the patterns were indexed at the standard card 44, 14, 17, and the effective grain size was calculated using the Shearer's equation. From there, we realized those are the patterns. The major diffraction peaks at 2 theta, that's the angle at 2 theta, they were at the angle of 24, and they were 24.24, 28.34, 28.84, 32 points. And these angles, the peaks were matching with the identified reflection planes of 0, 1, 1. Those were they were matching, and these peaks were matching so well with cacospite, the area of adorhombic in crystal structure of cacospite phase. We realized as the temperatures were increased, however, as the temperatures were increased at 300 degrees Celsius, and 350, there were other peaks that were appearing, indicating that there is a mixture phase that was there present, and I realized there is a phase of the tetrahedrite at the reflection at the 2 theta at 29.43 corresponding to a reflection plane 222 of the tetrahedrite phase. Therefore, as the substrate temperature of 190, 350, and 350, the grain size also increased as 14.76 nanometers to 23, and then to 29 respectively. This shows as we increase the temperatures, the crystalline phase also changes. From the NH dispersive X-ray fluorescent, that's the EDXRF, the elemental composition of the thin films were done. And the results from it, we realized that the spectrum were measured with the 3 targets, that's the RX9, the niobium, and the copper targets. And generally it shows that there is some escape peaks of copper at 1.75 and at 2.2 for at niobium, and at the escape peak of copper at sulfur at 11.3. So from the sample also we will be able to see from this that sulfur was present, which had 282,000 particles per million, and there was antimony at 69,400 particles per million, and there is presence of copper at 23,000 particles per million. Therefore, from EDXRF, it implies that the sample that I prepared contains copper antimony sulfide on that ratio. Therefore, it was copper antimony sulfide, actually the thin films that I prepared. So I did the morphology using the same, that is scanning electron microscopy, because it's a suitable and adaptable method to study the microstructure of thin films. Therefore, it produces the magnified particles, images of these particles and the patterns. From this, at A, we deposited at 190 degrees. And we will be able to see the images that reveal that the particles are agglomerated into a needle-like shapes. As the temperatures B, it's deposited at 300 degrees Celsius, whereby we'll be able to realize that the particles get arranged as times as we were increasing the temperatures. And at C, it was deposited at 350 degrees Celsius. Therefore,
Nancy,
yeah?
Nancy, you have 3 minutes, please.
Thank you. I will try.
3
Therefore,
minutes.
okay. So the particles, as the temperatures are increased, therefore the agglomerated needle-like particles get being, the morphology changes, so they get randomly arranged. So the optical properties, as the temperatures was increased from 190 to 300 to 350, the band gap also increased. So it started from 1.53 and ended at 1.93 electrovolts, showing that as the temperatures was increased, the band gap also narrowed, indicating there is the modifications of conduction band and the valence band as the temperature was increased. Therefore, we have the absorption coefficients. We checked also the absorption coefficients. As the temperatures also increased, it also indicated that the absorption coefficients also increases with the temperature. The same with the refractive index. As the temperatures also increased, the refractive index also varied. At some point under the UV, it is very low, while the extinction coefficient also increased with the temperatures. The electrical properties were done by simulations of the simulation using Scout 2 software, and they were fit with the spectrum in the system, and it showed, I used two models, that's the Trude model and the scheme oscillator model. And from it, I was able to determine the conductivity, the resistivity, and the mobility. So the conductivity was found to be increasing as the temperature was also increased. That's from 134 to 947 as the temperature. Carrier concentration also increased. It implies that carrier concentration increases with increasing substrate temperature. This is due to crystalline change with increase in temperature. Therefore, in conclusion, I successfully deposited copper antimony sulfide by varying the substrate temperature, that's 193.
Nancy, your network, you are going off. Are you? The network has, and Nancy has gone off. I think since she was actually just concluding on our work, I suggest that we proceed. Yes, I suggest that we proceed with question from question to the three presenters. That is, if you have question for Jorim, Alex, and Nancy.
Our 3-part course on building iOS mobile apps and macOS.
Sometimes people take half-truth and put them together, and then it creates a misdirection or a diversion. You would have to be blind and deaf to not recognize that what is happening is not normal and is not justified.
There is some noise in the background. Hello. Members, can you hear me?
Yes, I can hear you.
Yeah, I would request other members to kindly mute their microphone. And we have questions and discussion on presentation, which we have just had. So members with question, this is the time I'm calling for question. I would expect you to introduce yourself and speak clearly.
Hello?
Yes, please.
Mogunda Charles. I have a question for Alex Okello.
Go ahead.
It was good work for him, but I could also like to understand how he obtained the standard curve, the isolation procedure he did, so that we can ascertain that he got were actually the purity levels or the recovery percentages for the same compound. I believe I'm clear.
Dr. Okello, where's the chairman go?
Dr. Okello is gone. So Alex, can you answer that question? Alex.
Yes.
Oh, yes. I'm here.
Yes, I'm back.
Oh, you're back.
Yes, please. Sorry for that. Alex, can you answer, please?
I want to reshare the slide so that I can answer that question. It is taking long. Yes.
I was off.
Are you able to see that screen? Hello?
Yes, please.
Yes.
Yes, his question is how did I prepare the standard curve and how did I purify? I'll take you back through the process of extraction. Here I macerated fresh flowers of Acanthus pubescens in methanol, which was acidified with 0.5% trifluoroacetic acid. Then I filtered using glass wool, and then I concentrated it in a rotary evaporator. Now, the reason for concentration was to expel all the methanol so that you only remain with the water in the extract after filtrating with glass wool. Now, that filtrate, which contains, which is aqueous, it was partitioned against ethyl acetate. Now that after having partitioned against ethyl acetate, as you can see from this diagram here, I said earlier that the upper part contains so many compounds, which was discarded. And then it is the lower part which contains anthocyanins. That is where the purification of that dye ended, because we did not go through further details of isolating which particular type of anthocyanins, because my supervisor in chemistry told me that would be another PhD or master's altogether. So I stopped at that and used the extract there. Now, how I determine the standard curve, here we bought this compound here. This compound here, which contains anthocyanins. Then we measured these masses here, 0.014 milligrams, and so on and so forth. And then we used the same volumes, I mean the same solution of methanol, acidified 5%.
Online conference.
Then for each,
muted my microphone.
Then for each of these solutions which we had, we went ahead and we measured the absorbances at 530 nanometers. And then we plotted the values of absorbance which we obtained against concentration. And then I got this calibration curve, which has this equation. So this equation relates absorbance to the concentration. I hope I've answered you. Hello?
Yeah. Thank you.
Hello?
I can hear you.
Yes.
I'm satisfied. Thank you for your explanation.
All right, yes. Thank you.
Oh, thank you, Alex.
Hello,
any other question?
Victor.
Okay, Dari.
I'm Odari Victor, still on the same on what Alex is presenting. I wish to know if he was able to obtain an optimum concentration for his work, and if so, how did he arrive at it? Thank you.
Well, I wouldn't say I got optimum concentration, but it can be estimated from the performance. Okay, for example, I can pick one of the parameters of the solar cell, maybe short circuit current, open circuit voltage. And then I plot one of those values against concentration, and in that case, I would be able to obtain the optimum concentration. But I didn't do it. Hello?
Noted. Yes, this is Aduda. Can you comment on the stability of your solar cells made from the anthocyanin-based sensitizer?
Well, I also did not go ahead and I didn't go ahead to study the stability of the solar cells, but what I know, anthocyanins are very unstable compounds. Studying the stability of the solar cells required more time, so I didn't really do that.
Oh, can I comment?
Yes,
Yes,
Prof.
please go ahead.
Yes, a question has been raised about concentration, but Alex, you should be cognizant of the fact that, okay, in as much as the higher concentration would give you better results, but there is a technical problem of filling pores, and also dye being an insulator, the faker it is, that will also compromise the performance of the solar cell. So it is a delicate balance. Yeah, that's what I want to say.
I beg your pardon, maybe you put it in another way.
Oh, what I was saying here is this. Well, you measured the absorbance of dye
Yes.
as a function of concentration. Ideally, if you go on like that, you'll find that the highest concentration, which is almost 100%, will give you the best. But at higher percent, 100% concentration of whatever you have, say dye, it will not be possible for that dye to percolate into the interior complex porous network of your titanium dioxide. I think that's what you're using.
Yes.
So what I was saying is that as much as you would want to use higher concentration because they have higher absorbance, you will have a technical problem of filling the pores, right?
Yes.
And additionally, at higher concentration or at a thicker, higher viscosity of dyes, you are likely to make a thick layer of your dye, and that is not required in this case because for efficient charge transfer, you need essentially a monolayer of your dye on titanium dioxide. But if it's thick, you'll make a thicker layer. That's what I'm saying.
I've noted that, Prof.
All right, good.
Yes, we proceed. Another question? Going by some questions from the chat, I think they have been answered. There's somebody asking Jorim and Obila. I mean, Jorim Obila from University of Nairobi and Nancy Obare from University of Eldoret, where they did the X-ray results from. For Nancy, it has been answered. Maybe what about Jorim? Where did you do the X-ray results, X-ray analysis from? Is Jorim there? Okay, since Jorim has gone off, any other question, members? Which one? Alex, there's another question for you. Why did you prefer to use anthracite anthocyanin over other dyes?
Yes, I can answer that. At the beginning of the study, I had a discussion with my chemistry supervisor, and she advised a dye pigment whose structure is known. And because she had previously done that exact work, okay, her work was to extract the anthocyanins and characterize the type of anthocyanins. So because her being an expert in extraction of anthocyanins, and also because the structure of those anthocyanins were already known, we came to the idea that maybe I take that route of anthocyanins and use specifically those which are already known. Because if I was to go ahead and use other pigments, I didn't know the structure. For example, the attachment groups to the surface of TiO2 is not known if you pick any dye. So for better understanding of the work, it was advised that I use compounds which are known. Thank you.
Okay, thank you, Alex. Any other question? Members, I think we are done with this session. If there's no other question. Okay, this is just part 1 of session 2. We'll be going for lunch. I think before we go for lunch, I want to take you to Professor Mwabora. Maybe if you have some communication for that, then we'll be back at 2:30.
Yeah, thank you very much, Dr. Kello and the presenters for this session. We have kept time. Thank you, Dr. Ogacho, the rapporteur. You are very strict. So I hope the other rapporteurs will also follow suit from what the standard set by Dr. Ogacho. Well, the chair of the session said it rightly. We should be going for lunch, 1 hour break. So we should be meeting at 2:25. You all join so that at exactly 2:30 the sessions continue. Dr. Kello and Dr. Gacho will continue managing the sessions. But before we go, I think I want to recognize the presence of Daniel Egbe, the coordinator of ANSOL. Ansole, or is it Ansole or Ansole? He joined us. Professor Daniel Egbe, are you there? Can you just greet us 1 minute?
So I'm happy to be here. Okay, so through Victor Dari, so he posted it, the link in our WhatsApp group, the ANSOL WhatsApp group of Kenya, and I decided to register. So I'm happy to see most of the faces that I know already. Hello, and also Makora, and many of you, Francis, Msseesa, and also, okay, I'm not seeing Professor Duda, but he's hidden behind his microphone. Yeah, I've listened to the talks and they are very interesting. So I think also Bryce Richard is...
Egbe, I'm in, only that I've, now you can see my face.
Okay, okay. Nice to see you. So I think also Bryce Richard is also here. He will be giving a talk. He told me that he was invited to give a talk. So I hope next time I will be also invited to give a talk. So with time. So thank you for presenting me. And I said it's a nice meeting, and I think it's a good thing to continue on this path. So ourselves, we are organizing a webinar on Saturday in Germany. So you can also attend if you want. It's an international transdisciplinary conference in Africa. So I will send you the link for those who want to participate. It's also going to be an online conference. So thank you very much.
Okay, thank you very much, Daniel Egbe, for that. We also had, I also saw Professor Diale from the University of Victoria. I don't know whether she's there. I saw her, but if she's not there, maybe we can introduce her later. But is she there? Are you there? Prof. Diale from University of Pretoria? Okay, if she's not there, I think we'll introduce her later. So we can take a lunch break. So we meet at 2:25. Let's keep time, please. Thank you.
Okay. I'll to get me.
Brian, we're having problem getting you.
Brian. Brian.
Hello, me.
Can you use bundles if you are in Wi-Fi? If you are in Wi-Fi, I think it's not working well there. Can you use your bundles from wherever you are? But maybe, Chair Okello, I suggest that we go to the next speaker as we sort out Brian's issue. Chair Okello.
Okay, Brian. We shall get back to you after 15 minutes. I think let's go to the next presenter. The next speaker is Zaina Nasangu from Makerere University. Zaina, can you please share your screen? Share screen. What is it?
This is the one with the... What's the problem? It's working. Share presentation. Your presentation. What's your presentation? I mute the microphone. Presentation mode. This is F11. This is F11. F11. What's coming?
Hello, hello, Okelo.
Yes.
Zaina, she's having problems presenting. Can we present it from our side? She talks.
Yeah, I think
We
so.
project it? Huh?
You project it from that side. She's having problem.
Okay, fine. So let's project it, huh?
Yes.
Zaina, the sound is- So Zaina, can you stop sharing, please?
Stop sharing.
Zaina, stop sharing. Okay, fine. Okay, so.
It's going to.
You will find everything, but is your mic unmuted?
Yeah, it's unmuted.
Good afternoon, ladies and gentlemen.
Yes, good afternoon.
Good afternoon.
I'm Nasango Zaina from Makerere University, a master's student. My supervisors are Dr. Dennis Okelo and Dr. Nyenga Karidewa, Makerere University. My order of presentation, introduction, objectives, significance of the study, and then materials and methods. So my research is about determining the optical and electrical properties of thermally deposited aluminum thin films. I cannot control. Okay, please get back to the first slide. Okay, thank you very much. So my research is about determination of the optical and electrical properties of thermally deposited aluminum thin films. So in my introduction, a thin film is a layer of material ranging from fractions of a nanometer to several micrometers in thickness. And then thin film deposition, this is the act of applying a thin film of a material onto a substrate. The most common example of such is the household mirror, whereby we are having one surface reflecting and the other one is coated with a given material. Thin film technologies are a means of minimizing the cost of solar cells, because thin film solar cells are cheaper to manufacture due to their reduced material costs and handling costs. Then I chose aluminum as the material to use for making the thin film because it has very many coating, very great coating properties, like properties required for optical microelectronic and telecommunication applications. During the coating, I'm going to deposit my thin film using physical vapor deposition. Reason being, it is environmentally cleaner and produces a higher adhesion that is compared to chemical vapor deposition technique. There are also very many techniques of physical vapor deposition, but I will concentrate on the thermal evaporation for the film deposition. Then objectives of my study. My general objective is to investigate the optical and electrical properties of thermally deposited aluminum thin films. My specific objectives in this research are determine the effect of deposition angle on the optical and electrical properties of aluminum thin films. Then the other objective, I'll determine the effect of the target size on optical and electrical properties of aluminum thin films. Okay, then the significance of this study. As a result of the study, the knowledge I will have gained will help in the manufacture of reflectors for solar concentrators and solar cookers. Also, aluminum thin films will be used in electronics such as connections in semiconductors, integrated circuit devices, electrodes, and back contacts in solar cells. Not to forget, this study will improve people's standards of living through the invention of lighter, more advanced, more durable and stronger and more efficient products. Then materials and methods. The materials I will need for the study: aluminum wire, glass slides, ultrasonic cleaner, Eddy's Auto 306 vacuum coater, gently melt height 4-point probe, then a spectrophotometer, and lastly a meter rule. So I'll use the ultrasonic cleaner for cleaning my substrate to remove all the stains from it, along with distilled water, soap, and ethanol. Then the deposition, that is using thermal evaporation, will be done using the vacuum coater. Reflectance and transmittance of the films formed will be determined using the lambda 19 UV vis near spectrophotometer. Then the sheet resistance of the films will be determined by the gentle melt height 4-point probe, while the deposition angle, because I'll be depositing the films at different angles, I'll be using an angle rotator, and that will be connected inside the vacuum coater. And lastly, the size of the target I'll be depositing will be determined using a meter rule. Then for the case of thin metallic films, the electrical resistivity of the film, whose length is much longer than its thickness, will be determined using the expression below. Yes, using that expression. So whereby the V will be standing for the voltage in millivolts, current, I will be the current in milliamps, and the spacing between the electrode will be 1.5. Okay, then the expression below will be used for determining the thickness given the sheet resistance. So this is the schematic diagram for the deposition of my aluminium. So this is how my vacuum coater will be like. Down is the aluminium that I'll need to heat and then deposit onto glass. Then that will be the angle rotator to enable me deposit my aluminium at different angles. Then it will be connected to a thickness monitor as well as a chiller to cool the entire machine. So the target size that I'll be depositing at a time will be determined using a meter rule. Then for my data analysis, the data will be presented and analyzed using tables, graphs. Then the statistical parameters shall be compared for the deposition angles, sheet resistance, target size, reflectance, and transmittance. Now, those are some of my references. Thank you very much for listening. So that's what I so far have for my proposal.
I have a question. I have a question to ask you.
Hello. I don't
Yes,
know Dr. Keller is there.
Yes, I'm there.
Yes, I have a question to ask.
Zaina is done.
Zaina is done. There's somebody with a burning question. Probably you can ask that one as we go back to
I don't know whether there's a burning. Maybe I have two questions to the presenter. For first, our much appreciation for the nice presentation. But there is two things to ask on her specific objectives and on the data analysis. The first question: how will you use the tables to analyze your data? How will you use the tables to analyze your data? The second one goes to the specific objectives. Perhaps if I can see a slide is where I can raise correctly my question. If she can reshare the slides on the specific objectives.
Yeah, I think that somebody sharing from the specific objectives. Maybe she can state it. She can read it again.
Yeah, if she can read also is correct.
Yeah, you read.
Okay. Thank you for the question. About the specific objective, one is to determine the effect of deposition angle on optical and electrical properties of aluminium thin films. Yes. Then the other one is to determine the effect of target size on optical and electrical properties of aluminium thin films.
My question lies on the term effect. If we say determination of the effect of deposition angle, maybe that effect is the one which relates to the optical and electrical properties. Maybe you could restate by saying you are going to optimize the deposition angles to have the optical and electrical properties. So if you are saying the effect, that is the effect you are looking on the optical and electrical properties.
Yeah, I think she has taken note.
Yes.
She has taken note of that one.
Similar to the second objective, said to determine the effect. That effect is the one which will lead to the optical and electrical properties. Hopefully, should optimize the same to the first specific objective. That was on the first specific objective. On the data analysis, I asked how will you use the table to analyze the data?
Thank you very much. About data analysis, actually, Thank you for that correction. I did not be very specific, but the tables will help me to display my data. Then I'll use different softwares to analyze my data. Hello?
Hello. Okay.
Is it clear?
Yeah, it is clear. It is clear. Thank you too.
Dr. Okelo, this is Dr. Mnyati from University of Zambia. I have a comment and a question.
Please.
If you go to, I think it's significance of the study, where I think the benefits are indicated. I think in bullet number 3, the study will improve people's standard of living through invention of lighter weight and more advanced, durable, stronger, and more efficient products. Are you able to comment on how that is going to happen?
Thank you very much. About that one, because I've been basing on what is already in place. For example, if you look at, because when I look at nanotechnology, because my topic is under that area, we are looking at how we can make items smaller in size but perform more different activities. For example, if you look at the phone we started with, that big phone with a big aerial, but now the current phones that are ongoing in the market, they are very light and smaller and performing more functions compared to the phones that we had before. Similarly, when you look at the computers, the desktops were very big, the ones that were there initially. But we are looking as time progresses, as people discover more ideas in technology, they are making the laptops more compact, and yet they can perform more activities compared to the ones that were there initially. So in my study, I'll also be looking at something like that.
I think you should be very careful.
Okay, members, this was actually more or less a proposal. I think it is a proposal. That is why this work has not moved so much. I think she still has a lot of things to improve on this. I would suggest that we go on to Brian Owino and first give us his presentation.
Okelo.
Brian?
Okelo. Okelo, the chair of the session. Can I interject?
Yeah.
Yeah, discussions are supposed to come at the end of all the presentations. So
yes, Brian.
So Brian, I think we are presenting for him. Let's project for him and then he talks.
Okay.
Thank you very much. I'm present.
Let's project for you.
Okay, thank you very much, Chair, for the opportunity, and I must apologize for the technical hitch on my side. Now, I'm going to present this work, which is still at its proposal stage. Now, my name is Brian Owino, and my supervisors are Dr. Alex Ogacho, Professor Francis Nyongesa, and Professor Bernard Aduda, all from the Department of Physics at University of Nairobi. Now, the title of this proposal is Investigation on the Performance and Stability of cesium antimony iodide-based perovskite solar cells employing P3HT and copper thiocyanate for transport materials. So to the introduction part. Please move to the next slide. Okay, so the introduction part of this work. Now, why do we study solar cells? Somebody might be asking himself or herself that question. Now, currently, we are experiencing increase in global warming, which is as a result of combustion of fossil fuels. And also, we are faced by depletion of fossil fuels and also increase in global energy demand. All these has driven the need for improving on solar cells. Now, we have various generation of solar cells, which I'm not going to talk of at the moment. I'm just going to focus on perovskite solar cells. Now, as it has been said earlier by the previous presenters, perovskite solar cells, these are emerging photovoltaics, which they have low-cost material. They are made of low-cost material. They seem to possess high efficiencies, and also the fabrication process are simple. So to the next slide, please. Now, this table just summarizes the solar cell efficiency. It's solar cell efficiency for various photovoltaics. Now, our main interest is in these solar cells that we have something, a circle here, where we have a circle that is the perovskite solar cells. The current efficiencies, which stand at around 25.2, I think one of the initial presenters had mentioned that. So as we can see, the efficiencies for perovskites are improving, and it will be okay if we improve it much better, and also we work on the stability of this kind of solar cells. So can you go to the next slide, please? Okay, in as much as perovskites are promising photovoltaics, which might be commercialized for future use, they are faced with some challenges. And one of the challenges that are faced by the perovskite solar cells is the lead toxicity and also instability in humid conditions. Now, researchers are trying to work out on other materials that can be suitable to replace the lead, which is toxic. And in this case, we are proposing to substitute lead by antimony, which antimony shows suitable, I mean, it is stable towards moisture, and also it is also suitable to replace lead. Okay, let me just say that. Now, apart from that, we have in our work, we shall replace the methyl ammonium with cesium, which is effective for improving the stability compared to the common methyl ammonium that has been used previously. Okay, to the next slide. Now, also to have high-performing perovskite solar cells, we need to work on the whole transport material. Now, these whole transport materials need to be thermally stable. They need to possess high whole mobility. And as we know currently, spirometad, which is the currently mostly used whole transport material, possesses low whole mobility. And also it possesses poor conductivity. Now, to address this, we propose to substitute spirometad with copper thiocyanate, which has a higher whole mobility of 0.1 per square, 0.1 square centimeters per volume per second. Now, it also possesses suitable energy levels, and it is also affordable, and its synthesis route are very simplified. Now, the other whole mobility that we are proposing to look at is the P3HT, which exhibit excellent thermal stability and high whole mobility. Okay, to the next slide. Now, the objectives of this work will be, one, the main objective will be to evaluate the effect of introducing the two whole transport materials, that is the P3HT and copper thiocyanate whole transport materials, on the photovoltaic performance of cesium antimony iodide perovskite solar cells. Now, the specific objectives of this work are to design and fabricate the absorber layer using cesium antimony iodide as the absorber material, and then perform optical, electrical, morphological, and structural characterization of the active layer, that is the cesium antimony iodide perovskite. And then the next specific objective will be to investigate the role of P3HT and copper thiocyanate whole transport layers on the photovoltaic performance and stability of cesium antimony iodide perovskite solar cell. Now, finally, the last specific objective will be to assess the charge transport and recombination mechanisms of the fabricated solar cell using impedance spectroscopy and surface photovoltaic. Next slide. Now, onto the methodology part. Now, we will deposit various layers of the perovskite solar cell. First of all, we shall deposit the electrons transport layer, which we shall use titanium dioxide as the compact layer, and this will be deposited by spin coating technique. Now, after depositing the compact layer of titanium dioxide, we shall anneal the film. Now, secondly, on top of the electron transport layer, we shall deposit the active layer, that is the perovskite layer of cesium antimony iodide, which shall be prepared by co-evaporation of cesium iodide and antimony iodide in an evaporator. This will be performed in an inert environment, preferably in a glove box. Now, thirdly, we shall deposit the whole transport layer, that is the P3HT and copper thiocyanate, by spin coating onto the perovskite layer. Now, these two all transport materials will be deposited independently on the perovskite layers. Now, finally, we shall deposit a back electrode of gold, which we shall deposit by thermal evaporation. Now, this diagram, this one just illustrates the processes of fabrication of the perovskite solar cell, where we have the substrate, preferably the FTO substrate, and then by spin coating, we shall deposit the TiO2 compact layer, and then after that, we shall deposit the perovskite layer by cooperation, and after that, on the two layers, we shall deposit the whole transport material by spin coating, and lastly, we shall deposit the back contact, which is gold, by thermal deposition. Now, on to the film characterization and the solar cell characterization. Now, we shall perform various characterizations on the films and also on the fabricated solar cell. Now, we shall do optical characterization by UV-VIS spectroscopy, and then we shall study the structural properties of the deposited films by XRD analysis, and then the band gap shifts of the perovskite thin films shall be studied using photoluminescence. Deep and shallow defects in the films will be evaluated using photothermal deflection spectroscopy. And then surface electronic structure of the perovskite layer will be studied by X-ray photoelectron spectroscopy. Now, the current density voltage characterization of the fabricated cells will be performed using a solar simulator. Now, lastly, the charge and mass transport processes in the cell will be studied by electrochemical impedance analysis and also using surface charge spectroscopy. Okay, next slide. I think that marks the end of my presentation. This is just our work is still at the proposal stage, so I didn't have much today. Thank you.
Thank you. Mr. Ward, for your presentation. Now I think we are going to open for discussion. Are you getting me? Hey, the video is off. Yes, I said we are opening the floor for discussion and questions. And some other question we shall be using the chat if time doesn't allow. We just have 9 minutes to do this. So the time for question is open. Any question?
I have a question.
Yes, Lusato.
On the last presenter, particularly on.
Okay. Dr. Keller?
Yes, Odari.
I wish to comment on the presentation done by the first presenter, who is Mila Shatsala.
Go ahead.
I realized he was talking of having a fixed ratio of the methyl ammonium iodide and lead iodide of 7:3 because he read it in a certain publication that led to the high PCE. So my comment is that since he's in the proposal stage, he should not keep that ratio fixed, because probably he may not replicate exactly what was done by the other group, or probably a different ratio may lead to better results unless they have a full paper or report on the different ratios used when coming up with that layer. Thank you.
Thank you, Dr. Dari, for that comment. Next, there was somebody asking the last presenter. Who was this?
I wanted to ask him on his design and the fabrication of the absorber layer. Specifically, he has to say which kind of a design is he going to work with. And in designing, there are specific tasks that he's going to do. So in a particular task, he has to state now that I improve this and I do this one. So specifically, if you say design and fabricate, I see it's a huge thing. And designing being a specific, it is a huge, perhaps he's going to come up with a thing so interesting. To me, we needed to narrow it from designing what specific task is going to do in the designing. And that specific task, we need to obtain the better absorber layer.
Thank you very much. Thank you very much, Lusato. I think Brian has taken note of. I think if you look at that, it will help you improve on your proposal.
Thank you very much, Prof, for the insight. I'll improve on that.
Yeah, any other comments, members? Yeah, maybe. Okay, Charles.
Sam? Yeah, Charles Mugunda, University of Nairobi, PhD student. I'm concerned with the last presenter where he's mentioning use of gold. I believe we should also consider of that solar cell. Thank you.
Okay. I think, Brian, you need to take note of that again.
Okay, thank you, Prof. That is well noted. I'll take note of that, Mr. Charles.
Okay, members, I want to thank all the presenters for session 2. I think we have come to the end of session 2.
Professor Okello.
Yes, Milner.
Yeah, I want just to also say I'm grateful for the comment from Dr. Victor and I'm happy about it. Maybe a question to Brian, which I might also look for him so that we work together with him. He has mentioned that he is going to do his work using the glove box. I don't know if he has gotten somewhere where there is a glove box near us here so that we can work together with him.
Okay, thank you, Mila, for your concern. I think we can link up and see a better place where we can get the glove box and work together.
Okay. Thank you, Professor.
Okay, as I said, actually, we are closing this session. We are moving now to session 3 that will be chaired by Professor Nyongesa and rapporteured by Dr. Nuru.
Yeah, okay, I think there are changes there maybe.
Okay.
Professor Nyongesa is in some board meeting. You designated Professor Msseesa. Is Professor Msseesa around?
I'm back.
Oh, you're back. Okay, fine.
Yes.
So Professor Msseesa can chair this session. And then we have Dr. Nuru Mulyuka rapporteuring. And then Dr. Okello, I think the second part after lunch, you lost your rapporteur. But Dr. Odari, I think, took cover.
Okay.
So thanks.
Yeah, I'm sorry for that. I had power failure, but now I'm back.
Very good to note.
Yeah.
Please.
Question I just want to raise a
okay.
question about glove box. It is a piece of a setup we are proposing to buy in due course. So we hope we'll have achieved that as time goes by the end of this year or early next year.
Yes, Aline.
Thank you so much. Thank you.
Professor Msembi? Professor Msembi? The chair of the session, Professor Msembi?
Yes, I'm here.
Maybe before you begin the session, I think there's this Professor Diale from the University of Pretoria.
Yes.
She can greet us. I've seen her. I think she can greet us.
Okay, that's all right.
Yes, Professor Matse Muche Diale, University of Professor. She's one of the keynote speakers for conference. Professor Diale, are you there? Are you there?
She cannot communicate.
Okay, fine. If she's not there, Professor Msembi, you continue. I think we'll continue checking. Professor Msembi, continue.
Okay.